Now let us discuss about force on charge due to multiple charges. Okay, let us discuss this topic. Now you say, suppose we have a system of charges. There are n number of charges. Suppose this is a Q1, it is Q2, Q3, and so on. We have suppose n number of, this is suppose Qn, n number of charges, and displacement from suppose Q1 to Q2 to Q1 is suppose R21, and Q3 to Q2 be suppose R31, and from Qn to Q1 suppose Rn1. Okay, we have considered that way. So displacement from Q1 Q2 to Q1 is R21, and that from Q3 to Q1 is suppose R31, and from Qn to Q1 is suppose Rn1. So these are the displacements we have considered. Now we are to find the force on this surge Q1 surge due to the remaining charges on this in this system. Okay, so how to do that? Now let us find first force on Q1 due to Q2. So by Coulombs law, so we have already discussed in the last class. If you haven't watched that video, please watch that lecture first, then watch it. So here you see force on Q1 due to Q2, that is F12, is given by 1 by 4 pi epsilon naught Q1 into Q2 by R21 square of R21 magnitude, square of the magnitude of R21, and its unit vector is R21 cap suppose. So similarly we can find force on Q2, sorry not Q2, Q1 due to Q3, so then F13, that is force on Q1 due to Q3, is F13, that is given by 1 by 4 pi epsilon naught Q1 Q3 by the displacement is here in this case R31. So R31, its magnitude, square of its magnitude, and unit vector R31. So and that's how we can find forces on Q1 surge due to this remaining charges in this system. So F1n, that means force on Q1 due to Qn, that is given by 1 by 4 pi epsilon naught Q1 dot Qn by Rn1 square of its magnitude and Rn1 cap. That's how we can find. And to find total force, net force, so let me draw a line here. How to find the net force acting on this surge Q1? Okay, how to find that? So if we add all this, if we find the vector sum of all these force from F1 to F13, F14, and F1n, if we find a vector sum of all forces, then we will get the net force or total force on Q1 due to the remaining charges in this system. Okay, so force on Q1 due to all other charges, due to all other charges is vector sum of F12, F13, F14 up to F1n. If we add all these forces, then we will get the total force or net force acting on the surge Q1. Okay, so F total force is equal to F12 plus F13 plus F14 and up to plus F1n. So adding all these, we will get the total force on Q1 due to all other charges, right? So now what to do? So if you use these values here, if you put the values of F12, F13 up to F1n here, then what you will get? Then we will get F is equal to taking 1 by 4 pi epsilon common. We can take this part common from all these values. 1 by 4 epsilon naught, 1 by 4 epsilon naught we can take common, right? So taking that common, and here we will get also we can take Q1 also common. Okay, so here you can see in all expressions we have Q1, right? We can take Q1 also common. So let's take Q1 also common. Then what you will get? Q2 by R21 its magnitude is square, then R21 unit vector plus Q3 square of the magnitude of R31 into its 31 cap, R31 cap. This is the unit vector, and up to Qn by Rn1 square of its magnitude, then its unit vector. So that's what we will get, and it can be expressed as this way. Using summation, this result can be written as Q1 by 4 pi epsilon naught summation from I is equal to 2 up to n Qi by Ri1 square of its magnitude and position vector Ri1 unit vector. So that's how we can express the total force on the charge Q1 due to all other remaining charges. So this is the result. So hope you have understood this topic. Now let's move on to another topic. So now electric field. Our topic is electric field. So what do you mean by electric field? Suppose we have a charge here, maybe it is positive or negative. So let us take it as positive here. So there must be a certain region in which if you keep another charge, this charge due to which this field exists, so within that region it can exert force on the other charge in this field. So that is electric field in this region. So this is the region where a charged body can exert electrical force on another charge kept at that region. Okay, that region is nothing but electric field. So if you keep this surge outside this region, then this surge cannot exert force on this charge. So it must be within this region, and that region is nothing but electric field. So we can write the definition of electric field in this way: the region around a charge around a charge around a charge body in which it can exert force on other charge on another charge in that region is called electric field. Okay, so that is the definition of electric field. Now what will be the electric field due to discharge at a particular point in this region? Suppose we have a point P here. So what will be the electric field at this point due to this field? So in order to find that, I will move to next slide with if we keep one positive charge here at this point, the force exerted by the amount of force exerted by this source charge means for which the charge which is responsible for this electric field, that is source charge, and the charge which you keep at this point, that is our test charge. Suppose let us take a small q amount of charge is kept here at this point q, and this is capital Q. Suppose the source charge is capital Q. Okay, the force on this small q charge due to the capital Q charge will be given by Coulombs law, F 1 by 4 pi epsilon naught capital Q small q. If the distance between these two charges is suppose r, then that will be r square, then r cap, right? So this is the force exerted by the source charge capital Q on the test charge Q, and the electric field at this point P will be given by the force per unit area per 1 coulomb charge. Okay, force per 1 coulomb charge, that is electric field will be F by Q. So the force exerted on q amount of charge is F, right? So in q amount of charge the force is acting F. So on 1 coulomb charge it will be F by Q, right? So force per unit coulomb, that is the electric field at this point. Okay, so now let me write it in. Now let us suppose we have a charge here, this is capital Q, and then there must be an electric field around it. So let me represent it by this circle, red circle. So now we are to find the electric field at this point P. Okay, so what will be the electric field due to this Q charge, capital Q charge at this point? In order to find that, so let us suppose at this point P we have kept small q charge. So then the force exerted by this capital Q on this small q, and let us also suppose that the distance between these two be r, suppose, then according to Coulombs law the force between these two charges will be given by force F, that's going to be equal to 1 by 4 pi epsilon naught capital Q small q by r square r cap. In vector form it can be written this way, right? So now here you see this electric field that I have drawn here. For the existence of this electric field, Q charge is responsible. That's why here this Q charge is regarded as source charge, and the charge which is brought to this point P is test charge. Okay, so now you see, if F force acting on Q charge, on Q amount of charge, F force is acting, so then what will be the force on 1 coulomb charge? That's gonna be F by Q, right? So that's why electric field at this point P, okay, force exerted is nothing but force exerted by Q per coulomb charge. That's gonna be electric field E, that's F by Q, right? And if you use this expression here, then that's going to be equal to 1 by 4 pi epsilon naught capital Q by r square r cap. So this is the electric field, this is the expression for electric field. So let me write here. Electric field at P due to capital Q. And electric field is a vector quantity, okay, it has both direction and magnitude, and you know its SI unit is given by SI unit is Newton per coulomb, right? And dimensional formula is M L T to the power minus 3 A to the power minus 1. That is its dimensional formula. And so here let me add one more thing here. Now you see this charge, so this is the source charge. Now you see this electric field, existence of this electric field is due to this capital Q. So as we have brought this small q here at this point, so there must be also an electric field due to this surge small q, right? So we have assumed that this small q charge, this amount is very small, so electric field due to this charge is negligible. So we can write electric field E, instead of writing F by Q, we can write limit Q tends to 0 F by Q. Okay, so hope you have understood why should I write this. So how could you define electric field? So let me write the definition as well. So here let me write the definition of electric field at a point. Write the definition. So here you see electric field at a point in space. Electric field at a point in space due to a charge is the force exerted by the charge on unit positive charge, on on unit positive charge placed at that point, placed at that point. So this is the definition of electric field at a point. So hope you have understood this topic. Now let's move. Now let us discuss about electric field lines. These are straight or curved imaginary lines in a region such that if you draw a tangent at any point on that line, on a line, then it gives the direction of electric field at that point in that region. Okay, in that region. Suppose here you see in general this is a positive charge and this is a negative charge, suppose, and electric field lines generally comes outward, radially outward from positive charge and goes into the negative charge radially inward direction, in radially inward direction. And if you can draw this electric field line this way, from positive charge to negative charge, right? From positive to negative charge in this way, right? So this is a positive charge. From positive charge, electric field lines goes outward direction, in outward direction, radially outward. And in negative charge, this is negative charge, and start from positive and end at negative charge. In negative charge, if the negative charge is alone, then the direction should be inward, radially inward. If positive charge is alone, then direction of electric field lines should be outward, radially outward. So now you see, if you have a pair of charges, then start at positive charge, coming out from the positive charge and goes into the negative charge, like that. So here you see, if you draw a tangent, at any point on this line, suppose this is a point, if you draw a tangent here, this tangent from positive to negative, this arrow should be given such a way, it should be positive to negative. So here is the positive, this is negative, so I will give the arrow sign here, this in this direction. And at this point, if you have drawn this tangent will give you the direction of the electric field at this point, at this particular point. So here let us take another point. If you draw the tangent here, this will give you the direction of the electric field at this particular point, right? So that is about electric field lines. Now let us discuss the so first property, here you can see, of electric field lines. I have already explained this, that electric field lines emerge from positive charge and merge at negative charge. So this property I have just explained while discussing about electric field lines, right? So this is the direction of electric field lines, right? So for a single positive charge, electric field lines start at the positive charge and end at infinity, right? End at infinity. And for a single negative charge, if we have a single charge negatively charged, then start at infinity, and end at the charge, on the charge, this way, right? Radially inward direction. So I have explained those things. Now let's. So this is property number 2. Tangent at any point on electric field line gives the direction of electric field at that point. So suppose here you see, as we have already discussed this point also, this is the positive and this is the negative charge. So let me take one, I am taking one line here, and I am not drawing all the lines. So if you take a point here and if you draw the tangent from positive to negative, so then this direction of this tangent will give the direction of electric field at this particular point P, suppose. Okay, so that is the second property. Now next property says that two electric field lines do not cross each other, they never intersect each other. If they do, then what happens? If two lines intersect each other, then at the same point we can draw two tangents. We can draw two tangents, and two tangents means two directions, two directions of electric field at the same point, which is not possible. That means suppose this is an electric field lines, and there this is another electric field line. They are intersecting each other, or you can draw this way also. Let me draw black colored this way. This is another electric field line. Then if they intersect each other, then at the same point, here, at this point, you can draw two different tangents, right? So you can draw tangents for the black lines at the same point, and you can draw tangents for the red lines at the same point. And two tangents means two directions of electric field, and which is impossible, right? That's why any two lines, field lines, electric field lines, never intersect. Okay, so hope you have understood this. Now you see, density of field lines represents a magnitude of electric field. That means the field is stronger where the field lines are crowded. That means suppose let us take two regions. These are two regions, and here in the first region these are the field lines, suppose. Okay, and here in the second region these are the field lines. So if you compare the density of electric field lines in these two different regions, here the field lines are more dense and they are crowded. So here the strength of the magnetic field in this region will be stronger compared to this region, right? So here, because the density of the electric field lines is low and here density is high, that's why where the field lines are more dense and crowded, the strength of the magnetic field is high, stronger, right? So that's now our next properties are 5, 6, 7. Here you can see do not electric field lines do not form closed loop, they do not form closed loop. So here it is positive and this is negative charge, and this is electric field is emerged from the positive and ends at negative. It ends at negative. Okay, so uh, you cannot say this same line is coming out of the negative and entering the positive. So these two are different. Okay, so you cannot say they are closed loop, right? This is one line, this is another. So in case of magnetic field lines were closed loop because they emerge from north pole, merge at south pole, and inside the magnet and from south to north, right? In this way they were closed, but in this case they are not closed. So it just start from the positive charge and end at negative charge, and it is not continuous like this. Okay, remember that. And they are they are assumed to be continuous, they are considered to be or taken as continuous in free surge free region. In surge free region they are continuous. Okay, now sorry. So next property here it is given that electric field lines are perpendicular to surface of a charged body. Suppose we have a charged body here. Suppose we have a charged body, then if this is positively charged and electric field lines should go outward direction, right? But that should be gone out, that should be gone going out perpendicular to the surface of this charged body. So hope you have understood this point. And electric field lines do not pass through conductor. Electric field lines do not pass through conductor, right? Suppose if you have conducting wire and it carrying current I, so you can experience the electric field around the conductor but not inside the conductor. Okay, and but electric field lines can pass through dielectric materials. Dielectric materials means are those materials, those are not conducting materials, but they can store charge within it, within this material. Okay, so such kind of material are dielectric materials, and through such materials electric lines can be passed through. Okay, so hope you have understood. Now let us see the picture. Let us see the scenario what happens if two like charges and two unlike charges come close. So let me show you now. Now you see, suppose we have two like charges, both positive or maybe both negative, right? Maybe both negative. In such case, so electric field lines should go out. They should be going out of the of the going out radially of the charge from the charge, positive charge. So as these two are like charges, then what will happen? The lines which are going towards the other charge, these lines will be deflected like this. Okay, the scenario should be this, something like this, right? So this represents nothing but repulsion. So similarly in this case also, in case of negative charge also, you will see this scenario. You can see this picture. So this represents repulsion. So if they are unlike charges, positive and negative, the scenario should be like this. Right. From positive to negative, this way. Right. So this is attraction. Here it is repulsion. So hope you have understood this. So this is all about electric field and electric field lines. In the next class, we're going to discuss about electric dipole moment, and how a dipole behave in external electric fields. Those topics will be discussed in the next video. So thank you for watching. If you are new to my channel, please subscribe to the channel, hit the thumbs up button if you like it, and share with your friends. Help me to grow my channel. Thank you.